Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, I would like to do another exercise with you about joint probability density function, and we are also going to be using the concept of joint distribution function. Okay? So yeah, I really want you to be familiar with these concepts and to feel comfortable with them. Okay, here we go. This is the exercise that we're going to be working on. We are going to be doing together parts A and C. In our lecture notes, you'll find a detailed solution for part B. Okay, so let's do part A. Okay. So as you can see, we are given the expression of a joint probability density function up to a constant. So our first task is finding that constant, a constant such that this expression becomes a legit joint probability density function. Okay? So, what we know, right, is that this guy is 0 elsewhere. Okay, so the only region where we have a non-zero expression is in the unit square, right? So y1 lives between 0 and 1, y2 lives between 0 and 1 as well, right? Okay, so if we remember that theorem where we discussed the two properties that a legit joint probability density function must satisfy, one of them is that the double integral of the joint probability density function over the entire plane must be equal to 1. But in this case, that reduces to just the double integral over the unit square. Okay, so what we want is this: the integral from 0 to 1. We want another integral from 0 to 1 of our PDF, which is going to be k times y1 times y2 dy1 dy2. We want that guy to be equal to 1. And this is a constant, so we could factor it out here, right? And we can divide by k on both sides. So what we could do is finding this integral, and if we find that integral, what we're finding is the reciprocal of the constant that we need. So let's do that. Okay, let's find that integral on the left hand side. Okay, so this is not going to be too bad, right? First, note that we are integrating with respect to y1 first. So with respect to y1, y2 is constant. So we get to factor it out here. Okay, let me place it here outside, and let me place brackets for that integral that we have there. Let me see. Okay, let me just do this. Maybe it's going to let me. put those brackets that way. Okay. Now I want that dy2. Okay. So, makes sense? We just pull that guy out, y2, because that's a constant with respect to y1. Okay. So now that integral is something easy, right? It's going to be y1 squared divided by 2, evaluated here, 0, 1. Okay? So let me copy paste that. So now instead of an integral, what I'm going to have is just y1 y1 squared divided by 2 and we are going to be evaluating here 0, 1, right? Okay. Now, note that that will be just a beautiful 1/2. Okay? That's what we're going to end up with. So that's just 1/2. No need for these guys anymore, right? So now, since we have that 1/2, that's a constant, so let me pull it out. So it's going to be just 1/2 times that integral. It's just going to be the integral from 0 to 1 of y2 with respect to y2, of course. Okay, so that's going to be again nice integral. That's just going to be y2 squared divided by 2, right? And we're going to evaluate here at 1 and 0. So we're going to have 1/2 times something like this, right? But we have y2 here, and we're going to be evaluating here. But that's just going to be, in the end, 1/2. So we're going to have 1/2 times 1/2. That's going to be just 1/4. Right? But that happens to be just 1 over k. Therefore, the constant that we are looking for k equals 4. Make sense? Okay, so now we have a legit joint probability density function. Let's go back to what we want to do next. So we want to find this probability, the probability that y1, the first random variable in our joint probability density function, is less than or equal to 1/2, and then we want the probability that y2 is less than or equal to 3/4, right? Okay, now I want you to take a close look at it. Tell me, it reminds you of something that you have seen before? If we had only one of these guys, you would go, that seems to be the CDF of y1 evaluated at 1/2, right? Well, now we have these two guys here, and yeah, it's similar to that, right? So let me go back to where we have the definition of joint distribution function, right? So yeah, it's the joint distribution function. In this case, we want to evaluate the joint distribution function at 1/2 and 3/4. Okay, and now we also know that there's a way of computing that, and it's really similar to the way that you would compute, that you would evaluate the CDF at a point, right? Like before, but now instead of evaluating at one point on the real line, you evaluate at a point on the plane, right? So now instead of having a single integral, you have a double integral of your joint probability density function. But it's very, very similar. So let's try and do that one. Let me open a new page here. So what we want is the probability that the random variable y1 is less than or equal to 1/2, and that the random variable y2 is less than or equal to 3/4. Okay, so double integral, right, of our CDF, of our joint probability density function, right? Now we know that we have a constant here for y1, y2, and here we just have from 0 to 3/4. Well, it depends on which one you want to integrate first. If we integrate with respect to y1 first, it would be from 0 to 1/2. And then for y2, yeah, it would be from 0 to 3/4, right? Okay. So it's going to be easy. It's going to be very similar to what we did before. Note that we could factor out that 4. Let's place it outside, right? Now that y1, that y2 is going to be constant with respect to y1, right? So now we just pay attention to this integral here. Okay. And that's going to be just y1 squared divided by 2, right? So let's try to do this kind of quickly. So as I said, it's going to be y1 squared divided by 2, right? Let me write that down. Y1 squared divided by 2 and we want to evaluate, at 1/2 and at 0, right? So if we evaluate at 1/2, it's going to be 1/2 squared, it's going to be 1/4 times 1/2, it's going to be 1/8, and then minus 0 squared divided by 2, 0. So in the end we have just 1/8, right? Okay, now next step, since that guy is going to be a constant, we get to pull it out. So let's factor it out. Next, we have the integral of y2 with respect to y2. It's going to be y2 squared divided by 2, right? Okay. So what we have here is just y2 squared divided by 2, right? And we are evaluating 3/4 and add 0. So it's going to be 1/2 times 3/4 squared, right? Minus the evaluation at 0. But at 0 we are not going to have anything interesting, right? So it's just going to be 1/2 times 3/4 squared, right? So let me write it down like that. 1 times 3/4 squared. Okay? Okay. So let's do the math, and we're going to be done here. So we have here 4/8, it's 1/2 times 1/2, that's just 1/4. Agreed? So we have 1/4 times 3/4 squared, that's just going to be 9/16. Agreed? 9/16, and that's just 9 divided by 64. Okay, got it? Okay, now I just want to say something about that solution that I prepared for you in our lecture notes. So note that for part C, right, let me find where this problem is, 5.8, right? For part C, we just evaluated the CDF at this point, 1/2 and 3/4, and we just did that integral that I showed you. Okay, another way of solving that problem, and that's why we have part B, is just finding the expression for the joint distribution function, and once you have that expression for the joint distribution function, you just evaluate at 1/2 and 3/4. So here, as I said, I prepared detailed solutions for part B, right, and all the other parts as well, but the one that we have here would be this guy here, right? Case 4, we're evaluating at 1/2 and 3/4. Those numbers are between 0 and 1, so we have that integral here, and if you use that formula, you will end up with the same solution that we had doing it step by step. Okay, so anyway, please take a close look at that detailed solution for part B, so you become more familiar with these concepts of joint distribution function and joint probability density function. Well, that's it for now. Thank you so much for watching, and please take care and keep working hard. See you next time. Bye.